software performance engineering for the client graphics group at AMD. So we're actually responsible for working with our software partners to make sure that their software is optimized on all of the accelerators on our devices. So that's CPU, GPU, and now NPU as well. Joining me today is Nick Nee, who's responsible for product management in the AI group at AMD. So we're going to talk about Ryzen AI in terms of experience and in particular in terms of generative AI, which means LLMs and diffusion models for image generation. And we're not going to talk about hardware details, so we can answer questions, but we're going to talk about how to think about evaluating these things, what goes into the performance envelope and the experience envelope for users, and then we'll finish up with a couple of demos. So before we get into the details, let's talk about the AI PC experience, right? So we're in an industry that loves performance. We love to talk about performance, we love to measure performance, we love bigger performance, but performance is only one piece of the experience in AI PC. Obviously, the faster your model works, the faster you get the result, the better, right? It saves you time, you don't lose interest, you don't get distracted. But you can't run really fast at the cost of a lot of accuracy loss, right? So it's really easy to make an ML model go much faster by reducing the data type size, by reducing the model size, but when you do that, you lose accuracy. And when it comes to generative AI, when you lose accuracy, you get a lot of unknown side effects. Suddenly, the text you get back is just wrong, right? People talk about ML models hallucinating. They just make it up. If they don't know the answer, they'll just make it up. And the model will act like it's the truth, but it made it up. It's a piece of fiction. So when you have errors in your results, and now you have to check the errors yourself, now the tool didn't save you time, because you spent more time looking for the problems than you would have done if you'd written the whole thing yourself. So you have to have accuracy as well. The next thing you have to worry about is power consumption. You know, there's a lot of talk these days about how much power ML models are consuming around the world, right? Big data centers powered by huge numbers of gigawatts of electricity running. And when we run these things locally, you'd like to run them on your laptop. You know, you can't put a 350-watt GPU in your laptop. So if you want to run an AI experience like video camera processing, the last thing you want to do is to need a really big GPU or run on a big GPU. You want to run something lower power. And if you're lower power, then you generate less heat, your fans don't turn on, and when you're running on battery, you get better battery life. On the other hand, if you're running a filter in Photoshop, and that filter only takes 200 milliseconds, and you do it once, and then the next time you run it is 10 minutes from now, maybe you can run it on the GPU, right? Because the amount of heat you generated from one operation that's 200 milliseconds every 10 seconds is really minimal. So which accelerator you should use really depends on the type of workload you have, whether it's an always-on workload or something occasional, and also which accelerator is available at any given time. And then finally is the problem that everybody is going to start having next year, which is memory footprint. Today, people unitask ML applications. You load Stable Diffusion, you run Stable Diffusion, right? Just one application running an ML. So if you use all of your memory running Stable Diffusion, it's okay. Now with Copilot Plus and video effects that are using MPUs, and running Stable Diffusion, running LLMs all at the same time, now you have this problem that you want to have multiple very large models in memory. And the question is, does your accelerator support that, right? So consider mobile GPUs. Entry-level mobile GPU could be as low as 2 gigabytes of memory. That's not enough for a single experience, let alone multiple experiences. And even in the Ryzen AI PCs that are coming out this summer with Strix, you know, we heard Asus talk yesterday about 24 gigabytes of memory, which is amazing, right? It's a lot bigger than the 8 gigabytes you would have had 2 years ago. But what happens when you have a big LLM and you're running Stable Diffusion and Copilot's doing something else? all of a sudden you're consuming a lot of memory. And there are things you can do to tune the memory usage down, right? You can use a smaller model, you can quantize the data, or if you're AMD, you can use block float 16 to reduce the memory footprint of your models and still keep the 16-bit floating point accuracy. So all four of these comprise the AI PC experience. And this is what we think about, this is what we think about with our partners when we're discussing which accelerator should we use. Oh, you have this GPU experience today and you've had it for a year or two running on Radeon. Do we need that to run on the NPU? A lot of times the answer is no. It runs great on the GPU on Strix, and it doesn't need to run on the NPU to have great performance. And we know that they have new experiences coming that they want to run always on in the background. And we want to keep the NPU available to run those always on experiences in the background, right? So there's always going to be a mixture of different experiences running in different places as we balance the needs of performance, accuracy, data types, memory footprint, and power. So let's talk about LLMs in a bit more detail. There are actually two performance metrics in LLMs. The first one is the one people talk about a lot, tokens per second, right? We hear people talk about this, people ask me questions about tokens per second all the time. This is the kind of metric we love in this industry. It's a throughput metric. The bigger, the better. Come on, throw more power to get more tokens per second, right? I heard of some new piece of silicon that does 500 tokens a second or 1,000 tokens per second. It's really exciting. Can you read at 1,000 words a minute? Even 1,000 words a minute, not at 1,000 words a second. You can't, right? You don't need it to go that fast to be a good ML experience on your PC. You need to be fast enough that you don't, not always waiting for the next word. But in an AI PC, in a low power environment, we don't have to give up power consumption or battery life just to get more tokens. There's a level where it's fast enough, and that's an acceptable experience the users will be happy. But we can do things to tune this, and we have been doing things to tune this. For example, you can reduce the parameter size, right? Are you using Llama 2 70 billion or Llama 2 7 billion? Right? Now you can't run 70 billion on any PC laptop today, but you can run it on a Threadripper Pro, but you can't run it on a laptop today, but you can run 7 billion, and maybe you run a smaller model, consumes less memory, it runs faster, or you could start quantizing the model, right? So we go from FP32 to FP16 to int8 and now to int4. And when you see the demo we'll show you later today, that demo is running with int4 weights. So that's 4 times smaller memory footprint, 4 times less memory bandwidth required to run it, so it gives you less memory usage, very similar accuracy, and better performance. So that's tokens per second. And this will change from model to model, and depending on the sort of optimization that somebody has done, either in the framework that's running it or the model itself. So it's very difficult to compare 2 different implementations on 2 different platforms. You know, you need to make sure whenever you're comparing, especially for tokens per second, you need to run exactly the same workload. Otherwise, you're not comparing apples to apples. But time to first token is the metric I think is most important. What you find is, if I make you wait a long time to say the next word, your mind starts to think about other things, you get bored. And in fact, if you wait too long for the response to start coming back from your PC, you might actually change and do something else because you're fed up of waiting, right? So this is a metric, the responsiveness metric, that we really care about. And it's something that we've been caring about in other areas of performance, like with Microsoft Office and other things. Like responsiveness of operations really is what gives people the feeling of whether their PC is snappy or not. The problem with responsiveness is it's not a fixed metric. So when you run with an LLM, you give it a prompt. That prompt is the context, right? Context is the information that's being added to the model to process and produce the output. So if I start with a question which is 10 words long, now I have a 10 token prompt. And then the LLM may come back like this, very, very quickly. The LLM comes back with a paragraph, and maybe that paragraph has 100 words in it. The context the next time I ask a question through the prompt of the LLM is the original 10 plus the 100 it gave me plus my new prompt. So now maybe we're at 120 tokens. So we are now, our context size is 12 times bigger, which means the response time will be 12 times longer. It's a linear relationship, and this is true on any platform, including on the cloud, okay? The reason I'm telling you this is when you're evaluating LLM performance and you're looking at time to first token, you need to think about how big your context length is and make sure, especially when you're making comparisons, that the context length is the same. And when you're wondering why it's getting slower and slower and slower, you should clear the chat history, which sends your context back to 0, right? And that's just to make it easier for you to understand what you're measuring. You know, the user's experience, yes, it gets slower and slower, but that happens in the cloud as well, right? It happens everywhere, because now you're asking it to do a lot more work, because you're asking it to consider all of the words that were in the chat when it gives you the next answer. So just be careful about that. The other thing too, depending on the piece of software you're using, there can be a hidden prompt. So maybe you're trying to understand, hey, what's the time to first token for exactly 10 words? But actually there's a hidden prompt, something like, you are a helpful chatbot who is going to help me solve my problems in a very cheerful manner, right? That's a common type of hidden prompt, that when you type in your prompt, your application adds that prompt to it and then delivers the whole prompt to get the right behavior out of the LLM. So again, if this is the kind of thing that you're wanting to measure and you want to be very precise and have good hygiene in the way you measure things, think about all of these things. Now, everybody, AMD included, is working very hard to optimize these models. In addition, the models are changing every single day, right? And what that means is it's actually very, very hard, I'm afraid to say, to find a way to compare LLM performance numerically between two platforms. And in fact, there is no standard benchmark today. There are benchmarking companies and benchmarking standards organizations like MLPerf who are working on this problem. But I don't expect there will be a standard LLM benchmark available for the next 12 months, okay? So in the meantime, and maybe never, by the way, unless everybody can agree on, yes, this is exactly this model and this technique. And it's, as you've seen, it's a very complicated topic. So I think what I'm saying to you is, as you try to figure out how you're going to evaluate LLM performance, think about these concepts. Also think about accuracy, right? Whenever you're testing an LLM, have some standard set of questions, things that you can see the answer does change and sometimes it breaks, so that you can see when the model has been too optimized and you've lost too much accuracy, right? So you can make that statement. And you want different questions of different kinds. So definitely consider that. And then the last thing that I want to talk about with LLM performance and experience is there is a technique called speculative decode, which some of you will have heard about. Speculative decode is a technique where you take an original large model and you pair it with a small model that has been trained to match the large model. And instead of processing the large model all the time, we actually try and get most of the answer from the small model and then get the large model just to clean it up. It's an amazing technique, and we have it running in our research labs ourselves. But it is not the same as running the pure LLM. So yes, it delivers a great experience, but don't take a speculative decode implementation of an LLM and try and compare it to a non-speculative decode model on a different piece of hardware, because they're not doing the same work. And actually, we're seeing software vendors be slow to want to do this themselves. It's one thing to do this as research and open source, but for large software vendors, it This means that now, instead of training the single model, then now they have to double the amount of training they're doing for their own models. They need to train the small model and the large model and make sure that the two work together. So we do think we will see this technique come out and be used in applications from big household name software vendors, but it's not going to be soon. And you shouldn't try to use speculative decode implementations to predict how fast another application will be, because it's a completely different technique. And with that, let's just take a quick deep dive into the agentic RAG demo that Vamsi was showing yesterday. So what's happening here with the agentic RAG is we're using the LLM to go and fetch additional information it needs to know. So we start off with this question, right? Hey, what's the name of our new NPU architecture? And it came back and said RDNA. Well, that's no good. So that just means that the model, the way it was trained, didn't have that information in it. So the techniques that it's using here, the agentic part is the way that we can ask it to go out onto the internet and acquire new information. It takes that new information and it puts it in a database stored locally. This is called a vector database. And then when I ask another prompt from my LLM now, what the LLM does is it takes my prompt and it searches the vector database for information that seems to match the questions that I'm asking. And then it takes that information and it adds it to the prompt. Right? The same thing I've been talking about so far, the context lines. So in fact, and you'll see it, the time it takes to start responding is quite long because the prompt size that it's using includes all the information that it needs to answer the question. So it's a great example, A, of a technique which says you can make any LLM better by giving it more information in your context. But also, we're trading off performance for an incredibly accurate answer, right? And in this case, we had to wait longer to get the answer, but we got exactly the answer we needed because we gave it enough information to come along, right? So RAG is definitely a trending technique in a lot of LLM usage today, and we expect agentic workflows where multiple AI LLMs essentially work together to accomplish tasks, where each LLM is smaller and more specialized to be something that you see in a lot of applications moving forward. But you can see how it ties into the context length and then ties into the performance. Nick, I will hand it over to you to talk about Stable Diffusion.
Thank you, Chris. Hey, everybody. My name is Nick Nee. I'm from AI Group, and we in fact have two executives here as well, Sudeep and Rami. I'm assuming many of you came from Asia, so what is it, like 5 a.m., 6 a.m.? So thank you so much for being awake, and especially after the lunch, it's probably extra hard. So I want to make this session a little bit interactive, just to help you out as well, right? So again, Stable Diffusion, the good news is it's very visual, right? Like large language model is sexy, but it is text-based, right? But here it's very visual, and improvements become extremely visible, basically, right? So one thing I want to talk about is when you are evaluating something like Stable Diffusion, there are many things to consider also, but these are probably three main things that will make it apple to orange, something to worry about. So one is what kind of model this is using, right? This is a space that's evolving so fast, right? When Stability AI came up with the first version 1.5, it was less than 2 years ago, and it's already way stale, right? Since then, there was version 2.1, XL Turbo, which was a state-of-the-art model until 1 month ago, right? And at the Computex, actually, how many of you were at the Computex with the Lisa's keynote? Great. So, we actually had a great honor to invite Stability AI CEO on the stage, and we basically announced the general availability of 3.0, which people have been waiting for over 6 months, right? Because this model is amazing, right? It generates one of the most photorealistic images out there. So, and I'll show you some examples, but being on the latest trend is super important because this model continue to improve so fast. And many of the vendors in our competition continue to lag in 1.5 and 2.1, which very much still mainstream. Quantization, right? So we talked about integer 8, block FP16. I'll show exactly some concrete images and examples like why this matters and how we're fast. And then finally, CPU, GPU, NPUs, why we're trying to push as much as possible into the NPU from power efficiency perspective. So let's do some exercise, right? So I'll let you stare at this for 10 seconds, and I'll ask you which one you think is better. Okay, who votes for this one? Okay, who thinks this one's better? All right, so majority here, and you're absolutely right. This is the latest model, right? 2024, literally the Stable Diffusion 3 model, and this one's still not bad, right? This is using Excel from last year, and you can clearly see huge improvement, right? Exact same prompt that was given to the model. You see the background's much more authentic, the layouts are very clear, and especially one of these things, the text, is one of the most difficult things for the AI generation models. You can see it's very clear compared to the previous model, and also very natural, even with the wrinkle diffusion. And these are actually very difficult things that you can clearly see. This image a lot more useful than that other image when you start doing your creative work. So how about this one? Again, let's just stare at it for 10 seconds. Read the prompt too. Okay, so who think this one's better? This one? Yes, you're right. So this one's a little more tricky, right? I think the image itself is okay, except a few strange tails. But the important thing is the prompt understanding, right? This is important because as an artist, you don't want to just say draw a cat. You want to say much more, fine details, right? So describing more in detail and the AIGC model being able to understand it and actually translate that into a visual, in fact, is something very weak today in many of the models. So Stable Diffusion 3.0, again, improved that significantly. Okay, and then this is the one that we use at the Computex. I think many of you have seen that, right? I think this one is probably obvious, so I'm not going to do the quiz anymore. This is better. Clearly the finger's wrong and a lot of things are wrong. But even this one has some weakness. I don't know if anybody can spot some imperfection of this image.
The finger?
Yeah, a lot of people say that. I actually don't see that wrong. Finger. You mean here? Finger or? Here?
Yeah.
You think the thumb's too long? Or?
The thumb.
Oh, point. Maybe I didn't notice. Yeah. Anything wrong about this image?
No strings?
Ah, great. Yes. You have 7 strings. Right. So, and then actually the previous session I had even more fine print discoveries. But my point is, even these latest models not perfect, right? And there will be Stable Diffusion 4. There will be DALI 4. There's just continuous improvements in these models, and the improvement's so fast, right? So again, my point is, it's so important for a company like us to get to the latest, greatest, and this is why it was so strategic for us to have stability type partnership, and we launched the Stable Diffusion 3 together with the day 0 support. And you're gonna see a lot of demos running Excel turbos and 3.0s completely on the AIPC. Might as well just have some fun, right? So since Stable Diffusion 3 is so awesome, you can generate something so stunning. Now you can turn this into a video as well. Right, so this is also another open source model from Stability.ai called Stable Video Diffusion, somewhat similar to the OpenAI Sora type of video generation, but again, with a simple prompt, stunning image, and then into a simple video. Okay. So now let's talk about the data types. So this is something Vamsi has already talked about yesterday. Again, I want to show you some concrete examples, right? Integer 8, very good. 8-bit data type. All I need is 8 bits. I can cram so much more into my limited area of chip, and so I get the most compute. The problem is you do have to do something called quantization, which most of the ISVs and developers are simply not willing to do. It's definitely not as simple as some people want to say. You need a calibration data, and if you cannot meet the accuracy, you have to go back to the AI scientist team and ask them to do all sorts of complex stuff. Which, if your model is evolving every day, every week, you just don't have time for that, right? So, quantization is really difficult. Now, 16-bit is awesome data type, right? In most cases, you can get 99.9, close to 100% from FP30 to train data, but you just have twice more bits, so you can only fit basically half of the compute into the same area. So we're kind of fighting the physics here, right? Now, block FP16 sounds like a magic, but the concept is very simple. Now, if you're familiar with a 16-bit data type, there's two components, right? There's 8-bit mantissa and 8-bit exponent. What we saw is, in the AI space, a lot of adjacent numbers are similar. They share the same kind of exponent. So it's an overkill to have an exponent for every number. So we basically group them together. In this case, we group every 8 numbers with the same exponent. So you can do the math, right? You know, the exponent becomes 8 divided by 8. So basically 1 bit could represent all 8 numbers. So essentially you're reducing the bit from 16-bit down to very close to 8-bit, to be exact, 9, right? That's why you get the performance of integer 8, but also the accuracy of 16-bit, because you're not really losing anything for most of the numbers. And here's a concrete example where we're applying 0 quantization. So no quantization, same text. FP16 is very much close to the training data that we had. Training results with FP32. Block floating point 16, I challenge you to see the difference. I personally cannot tell any difference there. Very, very accurate. But the moment you do a non-quantization casting into the integer 8 with no calibration data, things just collapse big time, right? And this is just so visible with the vision type of models. Now, what you're gaining is, compared to FP16, you're gaining almost twice of the compute, simply because now we only have to process somewhere between 8 to 9 bit instead of 16. All right, awesome. And then finally, our goal, as you can see, is to move from CPU to iGPU and to the NPU as much as possible, right? And we're still very much in the evolution, in the progress here. But something like stable diffusion, we're already showing that we can move it to the NPUs and gain so much more power efficiency. Because it is optimized architecture for these kind of neural networks, while it has only a narrower span or workload coverage. But once you fit into the nice workloads, you're gaining huge amount of power efficiency, which is super important, especially the Copilot PCs, and there are a lot of these workloads will be running all the time, right? So you don't want that to drain your battery. So you want to move those heavy-duty tasks to the NPU as much as possible. Okay, so with that, let's finish up with the demo.
3 or 4 minutes.
Okay, so this is the point in these presentations where people turn around and say, hey, we're going to show you a demo. We're not going to show you one demo, we're going to show you 2 demos. And in fact, what we're going to show you here is our ability to do LLM and stable diffusion both very fast at the same time. And so we're going to run the LLM on the GPU, and we will run stable diffusion XL Turbo on the NPU. So let me start by getting a prompt. I'm going to copy and paste so I don't get myself into trouble by mistyping or misspelling a word. So the prompt is, tell me a story about an elephant in front of the pyramids of Giza. So I'm going to kick that off, and as you can see, it comes back with a story very quickly. And now I have a similar prompt here for the stable diffusion model, and that's running on the NPU. You can see the NPU kicked in there, and you can see we get a very high quality, great image at the same time as we were running full-on LLM, right? This is the power of the Ryzen AI 300 series, the ability to run 2 incredibly dense compute workloads at the same time and have great experience with both of those at the same time. Any questions? And while we want questions, just so you guys can see this is running on the NPU, I'll keep changing the animal. We can have a count. Yes, giraffe works great. Any questions? As you can see, it's very fast. Now this is Stable Diffusion XL Turbo. It's not the same as Stable Diffusion 1.5 that you're seeing in a lot of places that need a lot of iterations. This is only 4 iterations to generate this. If you're using Stable Diffusion 1.5, you'll need 18, 20, 25. So Hippo worked. Let's try something different. Let's try a Buffalo. That one didn't work out so well. So it goes to show every model has limitations, but you can see it's a great model. Yes, a question?
Well, when that NPU be used for generative AI in Stable Diffusion?
This is the NPU being used.
Yeah, when you release this for public, for the NPU.
I'm expecting that this will be available for you to try if you are doing a review of the Strix.
We can install.
Yes, you'll be able to install this application and download the model.
I think end of this month is when it's available, right? So I mean, basically reviewer time frame is when this will be available.
Okay, thank you.
I have a question. May I know if the LLM is working from the GPU or the NPU?
The LLM in this case was running on the GPU.
How does the system know which to, the NPU or the GPU?
applications are telling it
I see.
which one to do.
So technically the application developers have to define what kind of processes it's going to run.
Yes, they want to choose, and really application developers want to control the experience their users are having.
Okay.
And part of that experience is choosing the data type, right? So in this case, this is 4-bit, right? And we can do 4-bit and both, but some developers may have models that they only want to run in FP32, which means for everybody, every vendor, because no MPU has FP32 support, they would choose to run it on the GPU.
So
And we're finding our software partners want to know exactly where it's going to be run so that they can test like that in their QA processes.
So there is any specific API or framework to run with NPU?
Well, in this case, our recommended framework is Onyx Runtime. And Onyx Runtime it's a standard. It's driven by Microsoft. It's a standard. It works on every platform. And it makes it easy for software developers, and Microsoft provide very good optimization tools.
At the end, there is still GPU winning. Like if you're looking for
So as you can
APU,
see,
it should be looking
it's
for
quite
a
happy
good
doing
GPU.
any number of
Not
animals
NPU.
and doing it quickly and consistently running on the internet. Any other questions?
How much memory does the machine have?
This machine has 32 gigabytes of memory. And you can see that some of it is carved out and not showing up as available inside of Windows. And we're using about 17.5 gigabytes of memory for everything we're running at the same time.
Is it good enough for running the Stable Diffusion
Yes.
locally?
Oh, yes.
Oh,
And by the way, this Stable Diffusion XL Turbo running here is running with BlockFloat 16. So the reason why we're getting this performance and this level of quality is we're running the FP16 model using BlockFloat 16. So really you're seeing everything that we've talked about for the past 2 days on the screen.
Which industry do you think stands to benefit the most from this?
From machine learning technology or from Stable Diffusion? Okay, so I would say for machine learning in general, I think everybody can benefit from machine learning, right? It can help everybody in some way in their daily lives. But there are some very difficult computing problems that today require thousands, if not hundreds of thousands of hours of compute to come up with answers. high quality answers. For example, simulation, Elon Musk is sending all these rockets up, right? And the simulations that they're running to try and predict whether their changes to their design are going to work when they send the rocket up, that's a huge amount of compute. And partners that we have, like Answers, are already telling us and telling the world how they are training ML models using their simulators. And now they're able to use a machine learning model to produce an answer that's very close to accurate to their real simulations. And that is allowing companies who previously it might take them 6 months to find out whether their design is going to be good enough, to do it very, very quickly, right? So I think everybody benefits, but there are some places where the change in performance is so dramatic that you're going to see other improvements and other innovations made possible by machine learning.
Right.
Thanks so much, everyone.
Thanks, Chris. Okay. Our next session is straight at the end of the bowl.